So welcome everyone to our perhaps last talk in the seminar series in this summer. So today we're super excited to have Professor Anastasia Ailamaki from EPFL to talk to us about real-time intelligence. Professor Anastasia Ailamaki is a professor of computer science, well, computer and communications sciences at EPFL. So she's also a co-founder of the Raw Labs, a Swiss company developing real-time analytics infrastructure for big data platforms, especially those platforms that gather data from multiple different sources. So I don't think I need to introduce her too much, but she got her PhD from Wisconsin about 21 years ago in 2000. And she has received numerous awards, including the 2019 ACM EFCOD Innovations Award, and also a 2020 VLDB Women in Database Research Award. And among many other awards, there are also the prestigious Sloan Fellowship, as well as NSF Career Awards. And she has also received many Best Paper Awards. So we're really excited to hear what Professor Ailamaki is going to talk about today. So without further ado, I think the floor is yours.
Well, thank you very much. I trust you can hear me okay? Yes?
Yes.
Can you hear me well? Okay, great.
Yes, you can hear you.
This is great. Okay, thank you very much for joining, and thank you very much, Jen, for inviting me to this seminar. I'm excited to talk to you about real-time intelligence. This is the term I've been thinking as to describe decisions that I'd like to be making in real time, as opposed to the classic way of making them ahead of time. This isn't a real new concept, in the sense that a lot of people think, even in their daily life, but also when they're designing systems, well, let's not pre-decide this, let's do it later at runtime. What I would like to convince you about today is that this should be the norm, that we should not make any decisions about systems ahead of time, and rather we should find ways, aided by both good system engineering, but also with machine learning and artificial intelligence, to make all of our decisions about everything that constitutes important factors for our system's performance and functionality in real time. So narrowing it to data analytics, what I find that severely undermines performance is heterogeneity. And by heterogeneity, I mean diversity. I mean, everything that you have assumed to be one way, and it actually takes multiple forms and completely changes the game. So you can think about data formats, or you can think about data types, or you can think about applications, or even hardware. All of this introduces heterogeneity. But what I would like to show is how just-in-time data management, how just-in-time decisions with using data virtualization and code generation technologies, we have the technologies today that we can use to execute queries really fast across all kinds of inputs, of heterogeneous input, without costly preparation. Please feel free to interrupt me anytime with questions. Now, I'm going to try to see if I can. Okay, so we are faced with an evolving landscape, right? Back in the day, database systems were all general purpose that could answer declarative queries fast and efficiently, provided a single reference point for all the data, for example, of the company. And this one-size-fits-all system could provide a single source of truth for everything. It owned the data, low administration cost, easy database development, et cetera, et cetera. And then came the age of specialized systems. The one size does not fit all. But that gave us object-oriented databases, then OLTP and OLAP optimized, stream, graph optimized, array database management systems. And you got one system per data application pair, essentially, to the point that polystores and data lakes were built to handle the diverse number of systems found in modern applications. Now, the issue with all this was that ETL became really expensive, right? So we had to extract, transform, load the data. We had to coordinate across different systems. The diversity in systems created even heterogeneous data in terms of shapes, CSV, JSON, semi-structured, unstructured, diverse information issues like inconsistencies, constraint violations, etc. And these had to be handled globally, right? So, and lastly, due to the diversity further down the road, as we will talk about later, data generators such as sensors tend to produce really wasteful human readable data just to maintain portability. So now databases for machine learning and execution environments for function as a service are becoming commonplace. And this is stressing even more the integration and the overhead created by having to coordinate more systems. And each is handling their own data, their own workloads, and potentially having its own hardware preferences. And so this is shown in this graph already from 2016, which was 5 years ago. Forbes reported that only 9% of the data scientists' time is spent on mining data or patterns. The rest is spent on actually managing the infrastructure in the ways that I just mentioned, in integrating data and systems. So we really have been trying to rethink this landscape in order to both build more portable systems that will withstand the tests of time and heterogeneity, but also to increase the productivity of the data scientists, who are very, very highly paid people to do data binding. So I would like to show how the existing approaches that we have been using so far fail to handle heterogeneity because they are built on top of the technologies that we have, and that we need to rethink everything from the ground up. And I'm going to pause here and allow a philosophical, myself to make a philosophical point. This isn't really a surprise. Think of our societies or modern societies. The structures that we have been building are based on general rules. And these rules are based on assumptions that people are all the same. They look the same, they behave the same, they have some very similar characteristics. And we can see now with increased diversity in all possible dimensions, people find the structures to fail because the structures fail to abide by, it failed to embrace the diversity that people seek these days. So diversity is introduced today as a first-class need, and the solution isn't to patch what we have with additional features in order to address the diversity, because the diversities are only going to be increased and only going to be more multidimensional, but it is to actually build new structures without assumptions of uniformity. So this is really hard, right, to implement this in human societies. So I'm just going to talk about how we can make data processing systems real-time intelligent and embrace diversity in our technology. So what has changed? Okay, data size, structure, value, veracity, all of these has changed over time, right? First of all, data. As you all know, data sizes have been increasing. Data itself has been very diverse, and you've got all different data formats coming from all different data sources. And also, even more importantly, because we have many data formats coming from different data sources, and these need to be handled in order to provide useful information, a most important problem here is actually data sanitation or data sanitization or data cleaning. But not only data is diverse, what the other thing that's diverse is actually workloads. It's the applications. And the workloads, depending on the goal, you have totally different requirements, how these workloads will look, what kind of functionalities they will use, but also how fresh the data will be, whether they should include domain-specific tools like ML or biology tools or not, and all sorts of different workload requirements that are specialized, that serve specialized domains, change the way that we should be processing the data for those specific workloads. And last but not least, of course, the hardware is becoming very diverse, right? We have the new Franken chips now, which have totally different kinds of compute devices incorporated in them. And these compute devices are also changing. They become faster, they become more expensive, they come in different quantities, in different connections. So all the next generation systems must adapt in real time in all of the aspects of the change. And that's why the change means trouble. So this means that we've been talking about data-driven architectures, task-driven architectures, hardware-driven architectures. We need to produce change-driven architectures to survive heterogeneity, that's increasing in size and in dimensionality. We need systems that generalize the correct way in real time. So instead of requiring new systems that are built to efficiently handle each requirement, which creates all these integration issues, we need to create one architecture that can withstand these changes. Now, this is a complex problem, but in computer science, we learn how to address complexity through abstraction. So now is the time to abstract our architectures. And instead of hoping on one direct architecture that will do all, we should work toward a meta architecture, build toward systems that provide all the necessary flexibility and modularity required to provide the wished for capabilities, but customize themselves more for themselves at runtime to provide what's needed as efficiently as possible, making the correct decision when they have all the info. So the main insight here is that inspecting data and operations allows the system to find optimization opportunities that may not be generally valid, but are sound for the current configuration or workload or data or hardware. And this way we can get rid of unnecessary components and their overheads. And also we expose simplified and general interfaces that allows to handle complex operations without really complex systems underneath them. So I'm going to get more specific as we go, and first of all, let's just classify a little bit what we mean by heterogeneity, right? So as I said before, we have heterogeneous data and heterogeneous workloads and heterogeneous hardware. And this is just 3 of the dimensions. And these are challenges. I'm going to use this slide here to somehow classify a bit the problems, and through the problems we will see a classification of the possible solutions in order to achieve specialization not ahead of time but at runtime and embrace heterogeneity, provide these meta architectures that I talked about. And let's start from the data. What are the problems? Why is data heterogeneity a problem? Oops, sorry. Data heterogeneity is a problem because we have raw files and data formats, which are basically unstandardized formats. And then these formats mean that we should inspect the format and query at hand and reduce the problem to the specific query and format by generating a specialized engine. Right? Otherwise, if we assume a specific format from the get-go, when we receive different formats, then we have to unify all of the data and pay the cost of expensive ETL, or we have to use multiple systems and pay the cost of expensive system integration. Data, however, also have inconsistencies, right? So to produce a clean data set, a clean version of all of our owned data becomes more and more a utopia that's also arguably not really needed, right? So we need to find ways to only clean useful data and also embrace all of the possible errors, but also specific errors to the application that may not be issues for other applications. So try to have dynamically defined cleaning strategies for the data that are application driven as well. And then finally, skewness is a huge problem, especially when we try to build fast access, very classic fast access structures like indexes. And there, the right thing to do, again, to address the unpredictable skewness of the data is to just do away with indexes and try to build indexes in real time. And there's been work on that too, but try to really build indexes in real time when both data change, but also applications change, really requires a truly real-time perspective. So let's try to dive now into these challenges and see specific solutions about data. So as we said before, data growth is going up. This graph is from the EMC survey of 2020, and it shows that data grows exponentially, and owned data is actually a huge quantity that its growth by far surpasses the growth of our capability to turn data into useful information. So there's a lot of data that's never read, and there's a lot of data that never needs to be read. Nevertheless, the way that we build systems currently pretty much resembles this picture. We have loaded data, and then we will clean the database, we will tune the database, and we will query. I'll get into this in more detail in a moment. But the point here is that in order to be correct here at the query time as to the preparation we've done, we need predictability. We need to know what the query will be and what the data needed for that query will be. And that's something that we don't know. So the predictability essentially goes down as the data growth goes up. And what we need is to inform data preparation from the beginning in order to have the right decisions made about here and to have a good performance. So I'm going to argue that preparation kills discovery. And that's a big statement, but think about a scientist, say, for example, an astronomer who uses a database and has a bunch of data sets and has a database product, any database product, and needs to load the data. Okay, so this scientist is going to load the data. Then they need to use products that clean the data. Then they need to build indexes and material is used to tune the database, and that's the third step. Then they need to ask an analytical question. The optimizer of the database will plan for the execution of the question. And then finally, the question will be run and get an answer. All this time, the scientist has the question. They know what question they want to run, but they need to first make sure all the data is in place and the database correctly tuned so that the question is asked. And if you think about this in the way that it's really happening with iterative questions, where one question, the answer brings the next question and the answer brings the next question, yes, maybe you don't have to load the data every time, but new data comes in or new tuning is needed. But even here with the execution planning and everything, the questions one after the other, iterative hypothesis is very hard to sustain, and there's a lot of time in between. So the scientist is really it's not very easy to maintain the train of thought. But also, this is a very expensive process, right? First of all, the cost of this preparation phase, all of these steps that I described before query execution, grows with the owned data, not with the used data. And we know very well that the data that we use today, most of the data that we have today is write only. And the data that used today is maybe 15 to 20% in the best case scenario from the data owned. So planning is also very expensive, as we all know, ahead of time optimization, and often even it's wrong. So this is a similar pie chart like the one I showed before, but here shows what the database does, where this whole process, where time is spent, and a big, huge bunch of the time is spent in sanitizing the database. So starting from I'm going to be giving you a little bit of what the current, or what I call conservative view is, where what we do today or what we did traditionally, and then what the real-time view would be. And in this case, traditional execution engines, the problem is that they put the actual query execution at the center of the design, build an engine, everything has to adapt to that engine, right? And for handling, even current systems built for handling heterogeneous data sources like Spark, Presto, these are really well-known systems. They add the heterogeneous data sources in there and you can use them, but they're really, if you look closely, second-class citizens through plugins that perform the data conversion on the fly before the execution starts. This extends traditional architectures to facilitate operations like projection, push, or filter pushed out, but it still is a fine granularity, and sometimes even through designs that are customized for specific raw data. To really minimize the wasted effort, we need to adapt the execution engine to the input data, which allows fine-grained data accesses and conversion only when really is necessary. Instead of providing type mappings from the source format to the one preferred by the execution engine, we virtualize the data to allow input data to flow through the engine in their initial minimal conversion effort format, and for as long as it's beneficial, of course. Now, to accelerate queries that touch the same data or same data sources multiple times, we go ahead, in order not to do the work twice, we go ahead and we build positional maps. And that way we allow fast localization conversion to the important data points in files that are queried repeatedly. This way, the execution engine is built to operate on virtualized data, and it customizes itself continuously to the data at hand, and it only pays data conversion costs as it goes. So it's like a pay-as-you-go system. And just as an example, our system Proteus that we've built that implements this philosophy avoids this overhead, all of this preparation overhead by so here you need to transform all of the virtualized data to what the DBMS assumes as an internal format, and then ask the query based on what the DBMS has and provides. And instead, we turn things around to have the engine plug itself to the data and then de-virtualize the operations happening on the critical path. More specifically, the plugins, the input plugins that we have here, they basically resemble the real plugs. You don't change your system, you just put a plug at the end of the wire so that you transform the signal only when needed, right? So similarly here, we transform the data only when it's used in the query, and for performance, we use, for example, specialized indexes that are called positional maps. And these are built as a byproduct of query execution to accelerate upcoming queries to the same sources. And then we also teach the engine how to access and parse input data on the fly during the actual expression evaluation. So specifically about this one, while from the execution engine's perspective, all of the expressions are described using specific virtual types like bag, set, and collection times and expression times that uniformly encapsulate quantities from booleans, for example, to collections. Instead of paying the initial interpretation and virtual call overheads, the engine takes advantage of the runtime static calls to de-virtualize everything through code generation. So code specific to the data representation is generated on the fly using the LLVM compiler infrastructure to reduce the branches which are required by interpretation and the function calls required to call back into the plugin, and allow the compiler to pipeline and interleave different operations that would traditionally reside way too far away to interleave from each other to be able to be interleaved. So for example, in different functions. As a result, the final execution engine has a critical path of execution that is customized to the data formats at hand. These are that are used by the query and parses data as deemed beneficial instead of doing data conversions and internalization at predetermined stages. So this is the high-level view, and now let's of the query execution engine and how it changes the game a bit. So we don't do anything until the query shows up, and then we know what data we need to use and what we need to do with it. And I'm going to go right on the big problem here, which is the data sanitization, right? The data cleaning. And traditionally, as I said, cleaning is an offline, time-consuming operation that occurs before data analysis takes even place, and which requires a priori knowledge of the data set and also a prior knowledge of what kind of errors it needs to address at any given time. So existing solutions you find are either offline, cleaning everything a priori. The objective is to provide a version of the database that's clean and queryable, but with little information of what exactly needs to be cleaned or how it will be used, because there is no such information at the very beginning. And then you have online cleaning approaches that clean what's needed, but only for a limited set of sanitization operations. And that's the reason for that is that complex constraints like denial constraints, for example, may be way too expensive to check in real time. So cleaning also has a high cost. For example, in the general case, the denial constraints, it often requires queries, it often requires a Cartesian product, for example, meaning that any tuple that is cleaned without needing it incurs a really high overhead, and for no good reason. So existing offline approaches focus on cleaning full columns and tables. So these are analysis independent, and they waste effort on unnecessary data cleaning operations, as they don't know the exact filters and submitted queries, even if they know which columns are of interest. They don't know which rows are of interest. So we don't know which tuples to clean, making the difference between theta joins and Cartesian products essentially. So in the case when users do exploratory analysis, they need to extract insights from dirty data fast without having to pay the cost of cleaning the whole data set. So we propose an approach that intermingles data cleaning with exploratory data analysis and gradually cleans the data set. How? We enable the generality of offline cleaning with the efficiency of online cleaning. So we virtualize a clean database and allow queries directly on the virtually clean database, but in reality, it's a dirty database. It's just a virtually clean database. So essentially, we pretend that the database is clean, but we relax the queries to cleaning what is absolutely necessary for the current query and provide attribute level semantics where each attribute that participates in the rule can take multiple candidate values to avoid human in the loop issues, right? So, and this is another reason why offline cleaning is popular, because online cleaning needs quite often human in the loop. Now, the probabilities of the candidate values are frequency based, They're basically, we calculate them through frequency of values, and they're driven by the conditional probabilities of the functional dependencies. So focusing on our cleaning efforts only on the fine granularity data, which is required by submitted queries instead of cleaning in column granularity, really boosts the efficiency of the system. So essentially, we address the coverage problem of data cleaning with this box here, with the common algebra, right? We introduce a cleaning language with which users can express different cleaning tasks and optimize them uniformly using this algebra. This is an algebra that expresses all cleaning operations. Now, at the same time, since data cleaning involves also heterogeneous data formats, this is an algebra that's expressive enough to support the cleaning tasks over these various data formats. By expressing the operations in the execution engine's language, we also optimize the logical plan that we execute using statistics from the dataset. By this, we estimate the overhead that data cleaning adds to each query and determine whether to execute the cleaning task over the whole dataset or execute the cleaning task only over the query result. Now, to provide correct answers over dirty data, we build a plan. It looks like a matrix. It consists of both query and cleaning operators, and then we execute this plan in a way that relaxes the result of the query by bringing extra information from the data set that wasn't needed, but it's going to be useful to clean any dirty values that sneak into the answer. So we make sure that way that there's no missing values from the result, and we correct any erroneous entities this way. It might happen, however, that the rules are general denial constraints and involve arbitrary conditions among attributes such as inequalities. For example, you might have a rule that says Mary cannot get more money than John and pay less tax than John. So if there is something like that, then you could see, you would know immediately that either salaries of Mary or John are wrong, or the tax that is recorded that Mary or John paid is wrong. So in an offline setting, a common approach is to detect such inconsistencies by constructing the Cartesian product matrix required by the inequality self-join computation and parallelize it by dividing the matrix across different nodes. Right, so here, for example, both columns and rows are salary and cells represent the Cartesian product. In our approach, a query-driven setting, at each query, we check the subject of the matrix that's required to clean the query result. We provide the probabilistic answers, and then we update the data set to account for the fix and avoid cleaning it again in consecutive passes. Therefore, after each query, we have a finer granularity, which enables excluding non-qualifying subsets like the one for which the upper bound is higher and the lower bound than the lower bound of the other range, like the example. Now, the next part is indexing. And indexing is a huge chapter, and it's been researched a lot. Online indexing is very nice. It's very valuable because it gives you what we can't get with offline indexing, right? Offline indexing is query oblivious. We don't know the queries, right? So it requires predictions and also duplicates data, right? Especially, and then when you don't have control over the data, for example, for raw data, that really creates a problem because you don't know when it has changed. Access paths are often defined by user input and in coarse-grained granularity because it's all guesswork. Cracking, on the other hand, is very good as an online strategy, but it still requires extra space and coarse-grained, and is coarse-grained. So for what we can use here is the fact that often data in files is implicitly clustered, which means that there's either, because when we collect data, we collect it very often in a clustered way, which means that there is either some degree of sortedness or grouping of similar data in specific places, and I'll show an example in a moment, but also that the value of data varies significantly even between data in the same file. For example, consider extraordinary events that are more interesting, or outliers, or drill downs. To take advantage of these properties, we allow on-the-fly fine granularity indexing of the raw data on top of the original format. So we create virtual partitions and virtually, logically, if you will, split the data files based on the distribution of the actual values. The latter, this strategy, creating virtual partitions, also bypasses the issue that we cannot modify and physically shuffle files that we do not own, while it takes advantage of locality, of course, and skewness to efficiently represent and index values in real time. So as we also, last point here is that as we use fine-grained tuning, we can adapt, build, drop indexes on some partitions of the files depending on the data value for each partition. And that we can do transparently to the user in the query. So in this picture, the color variations, orange, green, blue, and yellow on the attribute column here represent similar data. So these are not the same values, but the red values are values that are close to each other, the green ones are close to each other, and so on and so forth. So we have a query that runs from top to bottom, and we take advantage of these data properties that I mentioned in several ways, in two ways mostly, right? First is enable data skipping. So keep enough metadata per cluster and access only the ones that are relevant to a query. This we call zone maps. And then provide fine-grained access path selection. So some clusters may not be frequently accessed, so building an index of them might be wasted effort. However, first we have to recognize these logical clusters. So this needs to be done without pre-processing, right? And I also mentioned that we don't really load the data, so we don't really know all the data. We only know them as the query accesses them. And we need to partition data as a byproduct of query execution, because everything needs to happen, even the partitioning in real time during runtime of the query. So we partition data into contiguous non-overlapping subsets. And here, for example, it's shown like this. And every time when we partition data, we make decisions whether to build an index, what kind of index to build, when to build the index, maybe drop the index based on budget, drop this index or another index based on budget. So when the first query arrives, for example, we collect statistics over the data, and based on those statistics, we will first calculate the number of partitions to split the data set. And these are the lines that show the splits right here. And then each subsequent query collects statistics separately for each partition and further may split partitions until they converge to a state not worth further splitting. And then we use different techniques depending on the cardinality of a given attribute. So for candidate keys, we will use query-based partitioning, where we decide on the number of partitions only based on selectivity and homogeneous partitioning, or and then once a partition is stable, we can start tuning. And the tuning has to make the decisions that I mentioned, what index to build and when to build it. So in this case here, we decide to build the B+ index for this part of the file, and then a Bloom filter for this other part of the file, and so on and so forth. What's important here is that the goals of the partitioning are to increase partition disjointness by reducing distinct values within a partition and uniformity, and by reducing essentially uniformity across the file, but enforcing it through the partition without removing tail values. And this is a partitioning approach that helps us build the basics for reducing data access by skipping data and indexing that is tuned to the actual data and query patterns, not some predisposed assumption from the beginning of the processing. So that way we maximize gain and also minimize index building cost and reduce query response time as if we had built a specialized index for this query from ahead of time. These are two examples of technologies that help us treat data, clean data, and tune data in real time so that we can move these operations to query processing time, and that way we make all these costly, we apply all these costly techniques only when we really need the data and only for the data that's needed. The other two issues that I want to talk about are workload and hardware. And I'm going to start with workload. Heterogeneity in workloads is really hard. And the number one reason is uncertainty. We don't know what the query will be. If the query needs the data optimally in row format, this is the simplest possible example, and the data is in column format, this is going to result in inefficiencies. So without query templates or workload information, we really don't have any tools to build the systems or to structure the data or to even structure the, even decide the temporary structures of the data that we use during query processing. So it would be really nice to be able to predict future workloads and then build samples and sketches and do approximate query processing, expecting these future workloads that we predicted, and then correct going back. Now, the other issue about workloads is not just the uncertainty, is the complexity. Again, taking very simple examples from queries, queries have a lot of dependencies within them. Think of nested queries, for example, that make optimization really difficult because we don't know what the values will be. And being able to execute these queries optimally a lot of times is impossible if we have to decide all of the mechanisms to address query complexity from the get-go. Instead, we can use speculative methods to execute queries and decide these correlations. And then we do that. As we do that, we can actually implement these methods and use them. And then when we fail, go back and correct our mistakes. So it's kind of a different approach here that allows us to move all of these correlations that we need to make when we optimize complex queries in real time. Finally, multiple queries. So traditionally queries have been few, but now we decide, we see more and more workloads where you have at the same time thousands and thousands of analytical queries running on the same database. And multi-query optimization is extremely useful in this case, but it's very difficult to realize for several reasons that I will talk about in a minute. So so costly optimization is really hard to avoid unless we do it in real time. So I'd like to talk about these things before I go to hardware briefly. Traditionally, approximate query processing, which I really think that is a huge opportunity. It's a key to moving forward and taming the immense data sizes, data volumes that we have. But unfortunately, not all workloads, the data and data are the same. So the approximations that we need can either be determined offline or they can be determined online. Offline approximate query processing requires pre-processing and workload knowledge. Online approximate query processing requires no pre-processing and workload knowledge, but it provides more modest gains because we need to do a lot of things within the window that we see online. So our real-time alternative tries to combine both the offline and online benefits. We observe the past to estimate sample or sketch benefits. So I'm going to call samples and sketches that we use for approximate query processing under the umbrella of the term summaries. So estimate summaries, the benefit under size constraints. So what we need to be able to do is build samples on the fly, but also be able to drop them on the fly and pay only for the samples that we deem useful for a specific range of queries, which is what happens when the user specified queries. It requires indexes to survive big sessions, and the indexes stick around forever, right? So what you want to be able to do is build all of the structures very similarly to the indexes that I mentioned before and drop them on the fly. It's just that you need different kind of information than you do for the indexes. But a pay-as-you-go summary creation while mitigating storage overheads is the key here. So this is a window, what we propose is a window-based prediction approach, which materializes and uses these materialized summaries. And we start very similarly to how online AQP would do this. We piggyback on the query optimization and inject summarization operators, such as samplers, for example, into the query plan after aggregation operators. And then the summarization operators must abide to the grouping requirements of the aggregation. Subsequently, then, we push the summarization operators over other operators deeper into the query plan. And there's a series of restrictions ruling all this pushing of summarization operator, but that's available in extensive bibliography. So you can do this correctly for the summarization operators. And then we store all of the sub-plans that prospectively produce summaries in a heat map. And the heat map is a key because it's updated with every query that's executed, and it stores not only the summaries, but also the statistics that the optimizer produces. For example, how much a sub-plan will cost, and then the prospective size of an intermediate result. So based on this access statistics, we calculate the prospective gains from materializing the summary for future queries. To do that, we use a cost-benefit model where the cost is the storage cost and the benefit is the performance gains that we expect. We try to minimize the benefit while abiding by the storage requirements, and thus we solve the constraint knapsack problem that emerges using a greedy approach. If we decide to materialize, to minimize the cost of the current query, we store the intermediate result in memory and just flush offline to a summary warehouse storing all materialized summaries. In order to decide whether we should materialize a summary or not, we just forecast future workload based on the future workload based on the window of the past queries. And the window size can be different sizes. We are deciding between different sizes. We can calculate ahead of time multiple window sizes and then move from one to the other. And this can be a small number, like three different sizes. So it's a simple approach. Essentially, it's window-based and allows us to really adapt the summarization mechanism to the future queries by just looking at the previous queries. So another issue that I mentioned is the complexity, intra-query dependencies. And here, the traditional approach to implement, for example, a nested query is to unnest the queries. However, it's really hard because this stage is essentially the query execution in a way that's not productive, right? You have to wait for details that may be proven unnecessary from one subquery execution to the next and to the next. And also there's specific barriers in the execution that break the sharing. So what you want to do is relax these dependencies, but the only way to do this is to actually treat this query execution as a crystal ball, which will tell you, will give you an educated guess of what to expect as the value that will come back from the subquery before the subquery actually executes. So it sounds like black magic, but it actually can happen because you can speculate specific parts of the query and then just focus on repairing them if you make a mistake. So the only thing we need to be careful about is to keep the overhead of the mispredictions really low. So as an example here, we have one outer query and two subqueries, right? And then instead of having the outer query wait for the result of the second of subquery 2 here, we feed it with an approximation of the output of subquery 2, which we compute much faster. How? Using AQP, as we discovered, as we described before. And then we guard its output to allow repairs before we return the results to the user. And then we use a specialized join, which is not really that complicated. It's called SV's join to compute the diff from the actual answer and push it to the guard to make the repair. The guard is essentially the operator that repairs potential mispredictions. And the diff is based on the actual subquery answer. So this really allows not only to increase the intraquery parallelism, but by running the two outer and the subquery in parallel, but also it increases sharing opportunities across the query because things are happening essentially at the same time. Imagine both the outer and the subquery scanning the same table, that will expose a lot of sharing opportunities. So we apply that recursively across all of the subqueries, and we maximize that way the parallelism and the sharing opportunities. So this creates on-the-fly task independency, despite the dependent nature of the queries. And this can be used in arbitrarily deeply nested queries because it can be applied at all of the levels. So last but not least, concurrent queries can be a lot, as I said before. So planning in multi-query execution is actually really hard. So the traditional approach is to share opportunistically. The problem, however, to share opportunistically means to look at the query that's in the system. If there's another queries another query that uses the same resources, then just have them share somehow opportunistically. But that's very costly. First of all, it misses sharing opportunities because queries might miss each other by a very small window. Second, it's actually dependent on different multi-query statistics, and it's very sensitive to query correlations across queries. So statistical information, even if you want to use statistical information across multiple joins or multiple queries, it's really known to be not as easy to acquire and also not as accurate to be useful. It results in diminishing returns, as it's been proven from multi-query optimization techniques. Instead, we'd like to merge the planning with the actual execution, pretty much like we did before with the data cleaning, for example, or the sampling. So we merge the planning with the actual execution to avoid the statistic generation holistically and also reduce the optimization time by creating a feedback loop between execution and planning. We have a system called Roulette, and it's called Roulette because it continuously goes around and round, doing a trial and error performance-wise, search of the search space through bandits that explore the search space and gains accurate statistics from the query trials that happen on the mini batches. Essentially, we use actual fine granularity statistics, and we allow the planner to have a go with a suggested plan without wasting that effort. So here's an example. Here's more of a schematic show of how Roulette works. what we want is to avoid the latency imposed by fetching. You have 3 queries here that come into the system, and you want to avoid the latency imposed by fetching a multi-query optimized plan for all the different disadvantages that that has. So the roulette accepts multiple queries and then quickly finds an initial plan and then spawns a mini batch for that plan. So concurrently, it gathers statistics about the join outputs and cardinalities and uses reinforcement learning. And this is where we get some help from machine learning to decide between exploring alternative plans or exploiting the currently found plan, and makes its decisions for the queries at hand. And then we do a multi-join that allows continuation across mini batches and essentially on-the-fly plan changes. So the plan we start with is this, guided by the reinforcement learning, but then guided by the initial plan, but then we change that plan using reinforcement learning. And then we avoid wasting any work. And the objective here is to maximize sharing. After a while, we converge to a plan that keeps executing until the end. That happens, except that happens in most cases, but this changes only if a statistic changes. So if we have correlations or patterns in the input tables, in which case it will reevaluate and re-explore alternative plans. So plan efficiency is guarded by reinforcement learning, and execution efficiency is guarded by low overhead adaptation. This concludes the uncertainty, complexity, and volume problem of the workload heterogeneity. And then similarly, and lastly, I'd like to talk for a few minutes about the underutilization, boundaries, and interference problems of the hardware. Underutilization of the hardware is a problem that me and many other people have been dealing with since a couple of decades now or more. And the problem is that hardware that we have in the machine is not utilized, but at a very small percentage because of different issues, task assignment, especially now that we have increased the explicit parallelism at the hardware level, or issues that have to do with memory hierarchy and so on and so forth. It's no use to try to address underutilization of the hardware in this CPU specific methods, because CPU memory hierarchies or CPU topologies are only one part of today's chips. Now we have heterogeneity in the hardware, and underutilization is a much more diverse problem. So an algorithm, in other words, an algorithm that observes good cache utilization of a CPU isn't necessarily going to give a good memory utilization in a cache of a GPU. Then at the same time, we have boundaries, and boundaries across different kinds of hardware, for example, GPUs and CPUs, which is a pair that I'm going to be using throughout this part just to showcase the techniques. Boundaries need to be obeyed because there are techniques that work differently across in different devices, but they also need to be easily crossed, because a lot of times the GPU needs to run a part of the query for which the data is next to the CPU, and so on and so forth. And this is very important for performance. This duality of tasks that are a lot of times connected or a lot of times conflicted is what creates the absolute necessity of real-time decisions. And then finally, interference, especially when we run complex workloads like HCAP on machines that involve different kinds of hardware, is a key issue to take advantage of heterogeneous hardware, what's called and taking correct advantage of heterogeneous hardware using the right way heterogeneous hardware is a subject of a big part of research that's called accelerator-level parallelism, also in computer architecture today. So without further ado, let's look at some ideas. Now you are used to me telling you, we're not going to make this decision ahead of time, but we're going to embed a couple of new operators to do cleaning or to do sampling or, inside the query plan. So we're going to do a very similar thing here. We're going to change the conservative operator scheme, which actually does something that makes it completely unusable in a hardware, in a heterogeneous hardware space. The problem with creating a plan and then executing it on a specific hardware is that, very simply, if your query plan is oblivious to the hardware, it's going to be very portable, but then your algorithms aren't going to have top performance on your hardware. If your query plan, your operators are hardware specific, they're going to be very fast on the hardware that you're running, but they're not going to be portable. So this performance portability trade-off across devices becomes an even more complex space to solve. Instead, and then all these other issues have, come into play. Operator implementations are device specific, load balancing that you can't predict how it's going to be, and it all results in inefficiency in the usability of the hardware. Instead, we follow an approach that's more data-centric. So it's an approach of scheduling resources in the system obliviously to the used devices and load balancing by inspecting in small granularity the flow across devices. So initially we're completely oblivious, and then we look at the flow across devices by deciding how much to use each device based on how it actually performs on the current query and data at hand. And then we guide the flow to the most appropriate device based on the throughput. So let's see how well this device does on this specific query and data. Let's see how well this other device does. So we gather some information there in real time, and we send queries and data to the different devices based on that information. Now, how we execute the query on this heterogeneous hardware infrastructure, that's through encapsulation, because we have to generate a query plan, right? And the query plan needs to be generated and executed. So instead of requiring full operator rewrite manually for each device, we virtualize the devices and we allow operators to share code across devices while they customize only some of their components per device. So this we do using code generation, and this way we remove the customization overhead from the critical path. And as an example here, I'm going to be using here also, I did that. I'm going to be using CPU for blue for CPU and green for GPU. Okay, so here you have a query that goes into a system that has both CPUs and GPUs. And a classic, so this query will do some work, we'll read some files, files, and then it will start filtering through and joining and doing this good stuff. We decouple the control flow. What we need there is to know how the data flows and how the control flows. The data is flow means from where the data resides currently, for example, a cache of a CPU, to where the data is needed for execution. That's the data flow. Now, and also how the data moves from one part of the plan to the next. Then control flow means exactly how the different operators are connected to each other, and when we need to go from one CPU to another, or from one kind of device to another kind of device. And that's control flow. Now, we decouple the control flow from the data flow, which are typically interconnected in classical query plans, by creating new operators. And these are the new operators that you see in red here. In gray, you see the operators that you will have in a regular query plan. So this poor query plan only had one filter and two aggregates, but we made it huge in order to be able to allow it to run on a system that has 3 CPUs and 2 GPUs. And here you have these parallelized onto 3 CPUs. Then right here, this operator, CPU to GPU, tells the system to go start running on the GPU. The GPU unpacks the information, and that's just because of different memory packings that happen in the CPU and the GPU. Then filter is run on the GPU. Then we pack back the information. We implement the opposite control flow, and we continue on the CPUs. Now, how this was generated isn't the subject of this talk. It was generated because this is the right load balancing. But you see, we have different new operators that we make that do either data flow or control flow, and we make them part of the plan that then is executed in the system. So you can do many optimizations this way. Now, the other issue that I mentioned, the second issue, is hardware boundaries. And the hardware boundaries is, these have to do with the fact that we have both kinds of hardware, different kinds of hardware, but also we have different kinds of applications. In here, very simply, you can think about device co-located OLAP and OLTP that just step on each other. So we use hardware boundaries to provide isolations, but just to make this really useful, we don't want to have static task assignments. We don't want to say that OLTP only runs on CPUs and never runs on GPUs and the other way around. And also we need to take care of communications. And here, just to provide with an example, you have a system that has some CPUs and some GPUs, and then you can have you have, of course, the connection to the DRAM, to your main memory, which provides for a very fast read-write operation. And typically, all of task parallel workloads like OLTP run on CPUs, and data parallel workloads run on GPUs most efficiently. However, there are a lot of times, say, for example, when you run HTAP, you need data to come from the OLTP side into the OLAP side, so that queries on the OLAP side run on fresh data. So how are you going to fetch fresh data from main memory to the OLAP side? Well, you may have a system that has a very fast NVLink that almost is as fast as this DRAM channel here, or you may have a much slower PCIe. The objective here is to not be dependent on specifics of the communication parts, but make decisions knowing the communication capabilities, so that when you need snapshot isolation, you can provide it for OLAP without concurrency control overhead, just because one link might be slower than the other. So, the last part of the system that I want to talk about is really freshness locality, right? So when we do static OLAP and OLTP assignment, for example, similarly to this really CPU-GPU interplay, interference is a huge problem. It's an issue in normal HTAP. But dancing engines, where engines are co-located or pulled apart based on the data throughputs, it's not really something that we can do anymore. In this case, what we want to do is adaptive scheduling of HTAP workloads. So we want to specialize to the requirements and data freshness rates. We want to do workload-based resource assignment, and we want to to have snapshot updates that are pay as you go. So this extends to general HTAP workloads, right? So where there are multiple options that trade off between performance isolation and performance to access fresh data. So if we need performance isolation, we go to something like this, where you have ETL that goes from one to the other and they don't communicate otherwise. If you want collocated, you go to an infrastructure like this. The point here is that it doesn't have to be one or the other. It can be something in between, right? So you don't want to be either on the extreme where you only invoke ETL to move information from OLTP to OLAP. You want to, or the extreme where everything accesses everything at the same time and interference becomes a huge problem. What you want is a hybrid designs, and you can have different hybrid designs, right? Which either provide compute isolation and provide fresh data access through delta accesses, and which is bottlenecked by interconnect bandwidth itself, or scales all up to LTP resources to provide this one, elastic compute, to provide processing local to the fresh data. So there is a lot of spectrum between the two extremes, and there's quite a bit of literature on building those. Summarizing all of these solutions, we see three trends. The first trend of solutions that kind of characterizes the solutions to these problems, standardized data, uncertainty of the workload, and underutilization, is inspect and reduce. So these are approaches that observe the query environment and produce solutions that are tuned to the problem and data at hand, either by crafting custom access paths, building appropriate samples, or generating device-specific code. Essentially, they specialize the executing instance to the task at hand. Now, the other kind of solutions for inconsistencies, for complexity, or for boundaries, they can be considered as relax and repair solutions. So these are approaches that attack the problem by solving a simplified version of the problem and then revise the answer to fix all the particularities or mispredictions specific to the task instance. And then finally, track and adjust to solve issues like skewness or increased query volume or interference. These approaches aim to resolve variabilities during the execution. So you have an execution that involves a lot of different stuff, a lot of different patterns. Instead of solving the worst case problem, you continue to observe the workload and utilization, and you take advantage of the special opportunities or runtime knowledge to fine-tune the system performance. So opportunistically, for example, building indexes on top of volatile, not owned by the engine files, right? There are raw files, raw data files residing no matter where. It's just based on the query, and you can do that in real time. So these are the three different kinds of queries. But the bad news is that we're not done. When we talked about data workloads and hardware, most of the workloads we discussed are similar to HTAP. But as we said in the beginning, we're moving towards a more heterogeneous landscape, including multiple workloads. So we see already a lot of work towards systems for ML, a lot of work, workloads that are moving to the cloud, serverless or function as a service models, et cetera, et cetera. So the application landscapes, so I'm going to change this to Chris, and I'm going to put a different unknown here that's called workload. The application landscape is going to change data processing even more. We have totally diverse modern data problems, right? We see workloads that start from IoT, ML, and databases catch up for popular functionality, but we're not really doing very well for all these medical problems, for example. Out of database workflows are not something that we're good at. And there's tons of information, right? But what we'd really like is zero-time integration of new functionality into existing systems. So self-learning systems is what we really need to produce. Everybody's heard of the V's, right? And these are the old friends that revisited. We can speak of variety as operational environment variety mostly. Veracity is really about intercomponent veracity, so heterogeneous data and variable importance of data, heaviness of data. Volume is really structural volume. That's the problem, right? Multi-layered system architectures. And then value is resource value. Analytics that are multi-featured, how they use the resources. Finally, velocity is technological velocity, right? How fast the hardware becomes volatile, heterogeneous, overturns any assumptions before. So the only solution to catch up with the evolving landscape is not to build intelligent real-time systems, but to build real-time intelligence in our systems. Change is the first-class citizen into our design, and we need to anticipate the change. We need to react, learning from the errors. And paraphrasing Amdahl's law here, I want to say, Amdahl says that a program sufficiency a program is only as efficient as its most serial component. I'm going to say that a solution is only as efficient as its least adaptive component, because that's where you are going to stumble. This is what I had to say today. Thank you very much for listening, and I'll take any questions.
Thank you very much for the great talk. I actually learned a lot. Are there any questions from the audience? You can unmute yourself and speak, or type into the chat window.
Yeah, thank you for the very nice talk. Yeah, learned a lot. So may I have one question about the data cleaning part? I think the idea of data cleaning based on the online query is great. Yeah, it saves a lot. But it also brings in probably one challenge and also one opportunity here is that if we have multiple users, and then how can the data, another person cleaned may be useful for me? How can I discover that? And how can I coordinate the sort of like multiple users collaboration in cleaning the data in new architecture?
So this is a great question. In all honesty, we haven't really done extensive experiments for multi-user environment, which actually is a very good, but we believe that this is I don't want to use the word easily, but it's doable to do through the other issues that I mentioned here. The reason why this chart for me, it kind of makes sense to me, this chart here, is that all of the techniques that you use, for example, here, they are being enabled, they are fuel. Then if you want the multi-user to work, you will fuel them with this part, with the volume part, for example. And you will make sure that your system here that does the sharing will do the sharing correctly, so that your cleaning agents that you put in your query plan work also across. So I like this orthogonality because it's a very regular shape, if you see it, and it's on purpose orthogonal, all of this to each other, right? So you don't want to introduce a technique that will overturn the efficiency of another technique. Rather, all of the techniques that we introduced are based on an algebra. Everything that you heard today is based on an underlying algebra, and that's powered by monoid category theory, monoid comprehensions, and it's implemented as a global way to treat all of these issues. So everything you want to do, your query ends up being an algebraic expression, which incorporates all of these. Now, when you do roulette, for example, to treat the volume of the query, or when you do prediction here, what we mean as query is the plan that contains also the cleaning operators. So all of the sharing work that we will do, we make sure that it also applies, and hopefully we do it effortlessly, right? Because if we do it right, so that it applies to all of the, because the functional language that we implement underneath in order to build these capabilities has as its first class citizen the orthogonality, which means if you have a capability for a query operator and you model a cleaning agent as a query operator, this query operator will immediately inherit all the capabilities of the others. So I hope I convinced you here that this is, and I'm not going to lie to you, we didn't do extensive experience with a lot of users for this part, for a specific one, but it should work with relatively few tuning issues in the software.
I see. So one follow-up question on this is that what do you think the pros and cons of versioning the online, data cleaning work done by users? Versioning meaning whether the user can, whether the system can provide users the capability to define different versions of their cleaned data or their queries, so that it's sort of like a middle granularity mechanism users can use.
So I happen to be a very big proponent of versions. I did my master's in schema versioning, and it was back in the day, and it was I think that data needs to be immutable. So like Pat Helen often says, immutability changes everything. I think versions are extremely important. I see them as different data. Once upon a time, many decades ago, Randy Katz introduced in the hardware the notion of configurations, which is, I don't know if it's actually different versions of different data that might not have been produced at similar times, but are connected logically together. So think of versions that are overlays on top of other versions. And this is what's really useful. What's really useful isn't the version of one data or even one table or even a bunch of tables. It's a version of the world that functions correctly because everything is done according to this version. This is defined at a very high application level. And we can do, I mean, this, if we attempt such a support at the level that I'm speaking now, because I'm a data access layer engineer, right? Everything else that I build here is built to aid, to provide functionality to the intelligent parts, right? To provide functionality to the cleaning. I'm not doing the cleaning, I help do the cleaning, but it still needs to be defined by the query what data it needs, right? How, and also because cleaning is a subjective issue, and I've talked to Ihab many times about this, and we have interesting differences in the views. For me, you may need the data with 2 decimal points, and I may need them with 3, or different normalizations for different machines. I mean, where you put the boundaries on subjective versus objective, like this is wrong value, right? That's a fact. It's actually interestingly diverse from one application to another. Given all these issues, a vertical integration, such as to connect essentially a very subjective application necessity requirement to this level of data access that I'm trying to make as versatile as possible, so the pipeline, the vertical pipeline, so if I vertically integrate all these levels, I'm going to lose tons of modularity in the system. So I'm going to say great, but it needs to be done higher. Yeah.
Thank
Very
you.
interesting question, though. Thank you. Yeah.
Thank you. Yeah.
I have a quick question.
Please.
I'm asking from the system perspective. So I know a lot of technology you mentioned here are already synced before, like adaptive query processing or the hardware software co-design. So one key information you mentioned is that we do a hybrid of many customized engine. So I'm wondering that how do we measure the system performance, because if we want to deliver a variety of workload but there's no such benchmarks and to measure each component, right? So I'm wondering that how we do things like that. Yeah.
Thank you, Anthony. This is a great question. I'm afraid I'm not going to make you very happy. I don't think we should measure system performance. I'm sorry. I mean, I grew up in a world where you would get, a bonus if your database was faster than everybody else's. But growing up, I realized that people had bigger problems than fast. Their major problems were that they can't do something. I mean, I worked on performance all my life, right? Before 2007, all of my work was on performance. And then I realized that people were not paying very much attention to me because, the problem was that they really couldn't do their work. And the problem wasn't that the system wasn't fast enough. The problem was that the system, they had 250 different database products to choose from, and they didn't know which one to choose. And there are so many other, and then they would choose one and they would just spend all of their time coding around the inconsistencies and inefficiencies of that and incompatibilities rather of that product to their problem, right? So I'm focusing here on trying to solve the functionality problem, and you will hear me say pay as you go and all that because I'm embracing the unknown, and yes, performance is important, but I'm going to decouple for now until we get this meta architecture, this real-time intelligence, we get this right. I'm going to be decoupling performance from functionality. I'm going to try to ensure that functionality is served in a way that's productive, even if any of the heterogeneity axes becomes more complex. And when functionality is served in that way, then I'm going to create engineering techniques to help performance in real time for the task at hand. But you're absolutely right, it's impossible to measure these things. At Raw Labs, we built such a system. The problem isn't how fast it is. The problem is that people feel most of the time that it's like magic. I mean, how can it execute a query if it has never seen the data? And, and the performance also is measured in, it's real-time performance in a sense, because you measure the performance of the first query and it's slow as hell. And then the second one is a bit faster. And by the fifth query, you run completely off of the caches. And then the performance is faster than any other system that you've ever met. But then if you go and you move to a different part of the data set that you've never seen before, performance is going to plummet again because I need to learn that part, right? So this is how it works.
Yeah,
it's a great question because it would be really nice for someone to work on this problem and see how we can measure performance on these kinds of systems. Thank you. Sorry.
I think we have maybe one comment from the chat from Aaron that big data is most of the big data is quite useless. So we should think about more on getting rid of useless data. I don't. So is this a do you have a specific question, Aaron, or it's just like a comment?
So may I say something about this?
Go ahead.
Arun, thank you very much for your comment. Comments are just as good as questions, because as you see here, I didn't provide a magic bullet for everything. I just am trying to do, to create, new database systems that help us think. This is a very important point that you raise. A lot of people in the community feel that data should never be deleted. A lot of people in the community feel that data should be deleted and the information about the data is the only thing that needs to be kept. Actually, a fantastic researcher, Martin Kersten, once published a position paper that's called the data fungus or something like that. The data with time grows fungus and gets destroyed, self-destroyed and all that. So, Tova Milo is in one of her latest talks. I think it was also in this seminar series she gave this talk. She doesn't like data very much. So, and I'm actually, I'm kind of, I think data, if you don't touch it, it's never going to be used. So it is going to disintegrate. It is going to be forgotten. Everything that's forgotten, like my diploma thesis at the university, it's written on software. It was about email and send mail and things that are now, defunct. And it's also written in the software. It doesn't work anymore. I can't find it anywhere, so I can't even open it. So it's gone, right? Now, if it exists somewhere and it's taking up space, I'm sure somebody will need that space and delete it without thinking twice. But this isn't the problem today. The problem today is how to make decisions based on our data that are reliable and timely. And the problem is becoming huge because people need these decisions. The world needs these decisions. We are now faced with a pandemic that has stopped us on our tracks. And we cannot not only predict what will happen, but we cannot even know what happens now. And if you read a book about that, Laura Spinney wrote a fabulous book about the Spanish flu of 1918 and how it destroyed it and how it changed the world. Rather, you will see that at that time in 1918, the Spanish flu killed more people than the First and Second World War together, right? And it was the same thing. It had the first wave that was bad, and then the second wave that was worse. And people didn't have internet, which was bad because they couldn't find out what was going on elsewhere, but it was also good because they couldn't find out what was going on elsewhere. And they didn't panic. And they treated the problem locally and in a distributed fashion. It's very interesting to compare the two and contrast them. So yeah, data is only important if they have something to say. I'd like to have the data from 1918, though, although it's been a long time. So I'm going to be respectfully in disagreement, calm disagreement with Don Knuth, as much as I respect him. But I think this kind of absolute, umbrella statements might be met with skepticism.
So I guess it's quite late as well. Do we have any final questions? Okay, if not, then I think let's thank Natasha again. Thank you for the great talk and staying with us. It's quite late. So
it's fine.
Yeah.
Thank you for giving me this opportunity. I was very happy to give this talk and research it. I mean, it's always an opportunity to think a bit deeper about what we do and why. So
yeah, great. So I would also like to make a kind of an announcement. So we are going to continue this series in the fall. As usual, you can always go to data.cs.svu/tdsa.html and typing it into the chat window. To follow our series, we will have, as usual, announcements and the past talks, recordings, posters on the website. So with that, I'd like to thank everyone for staying with us and see you in the fall.
Great.
Thank you very much.
Keep healthy.